Okay, so we're going to continue with conditional probability, and we're going to take it one step further and talk about something called Bayes' theorem. And a great example using Bayes' theorem has to do with a disease testing problem, which we did on the previous video. But let's do another one, and I change the numbers here. So let's say we have a rare disease that affects 1 out of 1,000 people. I think the previous one was 1 out of 250, so this is even more rare. A blood test is positive 99% of the time when the disease is actually present. So that's a really good number, right? That means 99% of the time, if the person has the disease, the blood test is going to correctly identify it. So that seems pretty good. And a positive test result will also happen in 2% of the cases when the person does not have the disease. So this is your false positive percentage, which is fairly low. That seems pretty good. I think the last one we did was like 5% or 6%. So these seem like pretty ideal numbers in terms of blood testing, but let's see what happens here. So first, let's find the probability that a random person tests positive if they take this test. So I'm going to let A be the event that the person has the disease, B is a positive test result. And like last time, we realize now that positive test results can come from people who actually have the disease and don't have the disease. So a tree diagram would probably be the best way to visualize this total probability. Okay, so probability of B, this branch is counting the people who actually have the disease. So first, the probability the person has the disease is 1 out of 1,000 times the probability that they get a positive test result given that they have the disease, which is the 99%. And you would multiply these together to get this very small decimal. We also have the positive test results from people who don't have the disease. So we could denote that as A complement, right? You either have the disease or you don't have the disease. So that would be 999 out of 1,000 people times the probability they get a positive test result given that they don't have the disease, which is 0.02. If you multiply those together, you get this decimal. So the total probability of getting a positive test result, you would add these two to get 0.02097. Okay. So we did one like that last time. And one of the questions then we were posing was, okay, so if you're the doctor and your patient does get a positive test result, right? It's not very likely, it's just over 2%, but if they do, they're going to be asking you, what are the chances I actually have this disease? Okay, and so this is the next question, taking it to the next level. If someone does test positive, what is the probability they actually have the disease? Okay, so what they're asking then, this is a conditional probability, right? What this is asking for is the probability of A that they have the disease given that they tested positive. And you'll recall we did the reverse conditional probability up here, right? That's the probability of B given A. So this is kind of the opposite conditional probability. So the idea of Bayes' theorem, the simplest version of this is this. It comes from, if you recall, the probability of A intersect B can either be thought of as the probability of A times the probability of B given A, or the probability of B times the probability of A given B. These would be equal to each other. So I enclosed this here because this is essentially, if you can remember this, that these two are equivalent, that's essentially what Bayes' theorem is, because what Bayes' theorem involves is that they're going to be asking for a conditional probability. And in this case, we're looking for the probability of A given B. So if you just solve like an algebra equation, solve for this probability, I would divide by the probability of B, right? Divide by the probability of B, and I have now a formula for the probability of A given B. The reason I really suggest if you understand this equation here, because other times they might be asking you for the probability of B given A. You might want this one here, right? And in which case you would divide both sides by the probability of A. So it's better if you know, if you can remember that, than try to use one of the formulas in the book, in my opinion. Okay, so we need the probability of A times the probability of B given A over the probability of B. Now you might notice that the probability of A times the probability of B given A, I'm going to slide this back up. We did that right here. That's this upper branch. So we already worked that out. That is 1 over 1,000 times 0.99. Then I have to divide that by the probability of B, which is what we worked out as our total probability of testing positive. And if you work that out, you get 0.0472, which is less than 5% chance that the person actually has the disease. Okay. So a couple of comments here. One, if you think about what we're actually doing, it makes perfect sense. If you want to find the probability that the person has the disease, you're basically taking the ratio, going back to this picture here, this was the percentage of positive test results from people who actually had the disease. And this was your total positive test percentage probability, right? So you're just taking the ratio of people who have the disease divided by the total probability of testing positive, right? So that makes sense. Second comment, if you're wondering why that's so low, right? It seems like, man, if you test positive on this test, blood test, you probably do have the disease, but this is saying that there's less than a 5% chance that you have the disease. It has to do with certainly the prevalence of the disease, because you think about it, out of 1,000 people, only one person is going to have the disease. And this probability, it's going to be, that person's going to most likely be detected, right? 99% chance of the time. Whereas because of the 2% false positive percentage on this particular blood test, that means out of 1,000 people, 2% of 1,000 is about 20. So about 20 people are going to test positive who actually don't have the disease, right? That's this number here. So you can see why that's so low. It's almost 1 out of 20, right? Roughly, right? That's why 0.04 is almost 0.05. So only 1 out of 20 or 21 people are going to test positive who actually have the disease, okay? So, all right. So then let's play doctor again here. Your patient just tested positive. You can, using Bayes' theorem, you can now come back to your patient and tell them, hey, I know you just tested positive, but the probability you actually have this disease is still less than 5%. Nevertheless, your patient is going to want maybe a little more certainty than that, right? So what would you do as a doctor? I would probably have my patient take the test again, okay, to see if they test positive again. So let's explore that. Okay, I'll just put this all up here. So what is the probability the same person tests positive twice? And we'll call 2B testing positive twice. Once again, that can come from people who have the disease, who don't have the disease. So we'll do a tree diagram here. 1 over 1,000. Okay, this comes back to the idea of the tests are assumed to be independent. The fact that you test positive the first time should not have any effect on the probability that you test positive the second time, which means the probability of testing positive twice, 99% chance the first time, 99% chance the second time. We multiply those together, 0.99 squared. For the people who don't have the disease, 999 out of 1,000. Each test is a 2% chance they'll test positive, so that would be 0.02 squared. Multiply those together to get this decimal. So the overall probability of testing positive twice for anybody, people who have the disease and don't have the disease, is really small, right? Less than 1%. It's not likely that anybody would test positive twice. But suppose your patient did, right? So now what they want to know is, what is the probability, given that they've tested positive twice, that they actually have the disease? And so that is, it's this right here. That is a conditional probability. That's the probability of A given to B, have the disease given that they've tested positive twice. And so this is what I would be thinking about, like I was saying with Bayes' theorem. That's a conditional probability. So the probability of 2B times the probability of A given 2B would have to equal the probability of A times the probability of 2B given A, right? In other words, just reverse them. This is what we're looking for. So we can divide by the probability of 2B. And where do you find these numbers? It comes back to this, what we did previously, right? This numerator is the top branch here. This is the fraction of the overall probability that came from people who actually have the disease. And then we're dividing that by the total probability, which is 0.00138. So when you work out the numbers, taking that ratio, it comes out to be about 71% chance now. So, right, that if your patient tests positive twice on this particular blood test, that means there's a 71% chance now that they have the disease. So that's very significant, right? That's okay. Yeah, and I say to students in 17 series, this, a lot of things we've done in the 17 series, I don't claim that you will, if you're going into the medical field, you may not use a double integral, or you may not do a linearization ever again. But if you're going to be my doctor, I want you to know this, okay? I want you to know that if I take a particular blood test, I want you to tell me, be able to explain to me the probability that I actually have a disease. So I think this is really, really important stuff to learn in the 17 series. Okay, I have one more example with Bayes' theorem. This one's not a biological example, but just to give you another scenario. Let's say you draw 2 cards from a deck of 52, one at a time. And the question is, find the probability that the first card was an ace, given that the second card you drew was an ace. And one of the cues, I guess, that you can anticipate using Bayes' theorem is oftentimes when you're using Bayes' theorem, they're asking for the probability of something that happened earlier, okay? In this case, they're asking, we draw our second card was an ace. They're asking for the probability that the card before that, right? Something that happened earlier was an ace. If you go back to the disease testing, you already tested positive, and then what a Bayes' theorem question would be, well, what's the probability that you actually have the disease? That would have happened first, right? You had the disease and then you test positive, or you didn't have the disease and you tested positive. So that's kind of a cue that you're going to be using Bayes' theorem. Regardless of whether you know that it's a Bayes' theorem question, it's going to be a conditional probability. So let's define A to be the probability that you get a ace first, B ace second. So what we want is the probability of A given B. And we know now that this is always true. The probability of A times the probability of B given A would equal the probability of B times the probability of A given B. This is what we're after. So we'll divide by the probability of B. Now the numerator we can work out. What's the probability you draw an ace first? 4 out of 52. What's the probability you get an ace second, given that you got an ace first? There's 3 aces left in the deck and 51 cards left in the deck. So it'd be 3 out of 51. Now, we have to divide that by the probability of B, which is the probability of getting an ace as your second card. Okay? But what you have to now think about is the probability that you get an ace as your second card depends on whether you got an ace as your first card or you didn't get an ace on your first card, right? Depends on your first card being an ace or not. So to compute this probability, you're going to have to use a tree diagram. Well, yeah, you're going to have to compute the total probability, whether you use a tree diagram or not. Okay, so then we're looking for the probability to get an ace second. This branch is the probability to get an ace first, which is 4 out of 52 times 3 out of 51. That's actually your numerator here. And I just multiplied 3 times 4 is 12, and then just left the denominator as 52 times 51. You could have also gotten an ace second if you didn't draw an ace first, which would be 48 out of 52. And then the probability to get an ace now is there's still 4 aces in the deck, but 51 cards left. So you multiply those together, you get this. So the total probability now, you would add these together. That's what's going to go in your denominator here. Because remember what we're doing is we're going to take the ratio. This is ace first, ace second, and we're going to divide that by the total probability, which is the sum of those two. So here's the numerator there, and then there's the denominator. What I did was, what did I do here? Oh yeah. So we're going to have to combine these and then flip and multiply. So I flipped and multiplied, okay? And I'd have to do, the denominator's the same, right? So I put 52 over 51 here. That's going to cancel with this denominator. And then to figure out what 12 plus 48 times 4 was, I just factored out a 12. And that leaves you with 1 plus, there would be a 4 left here if you take out a 12 from 48, and then the other 4, which is 16. The 12s cancel, so my probability is 1 out of 17. Okay.